So we're going to start by introducing you to radians. Anybody ever heard of radians before? You might have been like, why is my calculator not working? And someone will be like, oh, it's in radian mode. That might be the only place that you've heard of it other than grade 11 if you did learn some there. But basically, radian measure is a way of giving... Does anybody know why there's 360 degrees in a circle? Because there is? That's not a bad answer, actually. But the Babylonians, I don't know if you guys heard of them. I'm pretty sure it was them. They had calculated 360 days for the Earth to turn around the sun, which is not bad considering how long ago that was. So one rotation around, right, make one circle, and that became 360 degrees in a circle. So it was kind of arbitrary and incorrect, I guess. But radians are actually based on some real measurements, some real quantities. So it's pretty simple. Let's take a look here. What's the circumference of this circle here? Do you guys remember how to do circumference? Okay, good. 2 pi r. So what do you get for the circumference of this circle? Oh, good. Okay, so 2 pi. Radian measure, it tells us the arc length that the angle makes. So for example, if I wanted to tell you how many, instead of saying 360 degrees, I'm going to tell you that there's 2 pi of arc length here. There's 2 pi radians. Okay. Now, so if we don't want the whole circle, how do we make these adjustments? So if the radius is still 1, does this make anyone feel like eating pizza? Okay. What do you think? How many radians, that means how long is this piece on a circle with radius 1 if you know there's 90 degrees here? Pi over 2? That is correct. How did you get that? Yeah, it's a quarter of your pizza, and the whole pizza we just said had 2 pi. Sorry for the lame grade 6 references, but 45 degrees, anyone want to take a shot? Pi over 4, yeah, there's going to be pi over 4 radians there, so you're already getting the hang of this. And this one I think is the most important one. It's the one I refer to the most. Pi, yeah. So 180 degrees, we would consider that pi radians. By the way, the real world uses radians. Degrees is just more friendly to, you're not going to teach a 6-year-old about pi. Degrees are just easier to work with. So basically, the majority of this course and 100% of when we do calculus will be with radians. Okay, so to do these conversions, we definitely want to have a strategy, a bit of a better way of doing this. Oops, sorry. I guess I did leave a spot in the notes. Usually I'm pretty organized, so you don't have to double up, but there you go. The thing is, we just said 360 degrees is 2 pi radians. So, does anybody remember how to do 1 degree? How would you rearrange that equation? Yeah, divide by 360. So you're going to have 2 pi over 360. But of course, we're not going to work with 2 pi over 360. Usually we're going to work with pi over 180. And we can also go the other way. If I want to know what's 1 radian, then we can flip things around here. This would be 360 degrees over 2 pi. And again, most often we're going to refer to it this way, 180 over pi. Just simplify the fraction down. So the key thing that you want to remember is 180 and pi make the connection. And I'll give you the strategy here to help you figure out which one you're going to use. Radians have a pi in them, so when you want to get into radians, pi is on the top of your fraction because you're multiplying that pi in. When you want to get out of radians, you divide by pi to get rid of that pi. So pi goes on the bottom when you want to get out. So let me show you what it looks like here. 270, if I want to convert it to radians, I'm going to multiply in by pi, so it's going to go on the top of my fraction. And 270 degrees would be 3 pi over 2. Now 315, same thing, multiplying by pi, divide by 180. That way there's going to be a pi in my answer like radians usually have. So 315, anybody know what that's going to be? Simplified? Yeah, that's 7 pi over 4. Okay, and then finally, just because, I don't know, it seems boring, I guess we'll have to add an extra one in there. What do you think? 240 degrees in radians would be? Yeah, 4/3 pi. So 4 pi over 3. Now this time, okay, so if we go the other way, this is what I mean by there's usually a pi in radians. You're going to multiply by 180 and divide the pi out of your equation. So that's how I remember that pi goes on the bottom, because it's going to cancel out. I'm going to be back into that friendly world of degrees. Okay, so same thing. If I've got the pi on the top for radians, it's a helpful reminder that when I do my conversion, I want it on the bottom. All right, and then finally, you're not always going to get a nice perfect number like that. So we'll just try one here in case you've got a decimal. Not that I think it'll throw you that much. Oops. 1.57 times 180 over pi. So I end up with about 90 degrees. So it's like 89.95 degrees. Yes? Yeah, so that's a good point. This is what I did in my calculator. I just did it in the calculator instead of on the sheet. Or are you meaning it's not 1.57 pi? Okay. Yeah, pi doesn't always have to. That's a good point. I could still have a measurement like 2 radians or 1 radian. But for most part, we deal with some exact values. You're going to see pi in there. The way you know if you're working with radians or degrees is degrees are always marked like this, right? It's the radians that, if I gave you 2 choices, like 20 degrees versus 3, this one here is in radians because there's no units. Okay. So yeah, sorry, I shouldn't have said it like it has to have a pi in order to be in radians. Okay. Okay. So we can use radians for things like arc length. Okay, so A is going to be the arc length. R is going to be the radius of the circle, and theta is the angle. And here's the tricky part. It's always in radians. So the way you can think about it, right, is if I was to say give you one of those sections again, right? And I had like I can use that one, 60 degrees. And I asked you for the arc length there. That would be in this case, since it's a unit circle, I'm really just asking you for the radians. So radians are the arc length. The only difference is you have to scale it up by whatever the radius is. When the radius is 1, it is just the value of the measurement in radians. But if I was to double the radius, that doubles the length of the circle too, the circumference. Okay, so we'll try one here. Like if I told you that I'm going to create an arc that has 8.2 centimeter radius and 3.5 radians is the measure of the angle, then the arc length is going to be 8.2 centimeters times 3.5. So that's 28.7 centimeters. And if I told you it had 125 degrees when it made its arc, you just have to be careful because there's this temptation. This tablet is not cooperating right now. 8.2. There's this temptation to do that, but you're not talking about arc length because you're not in radians. So what we want to do is take 125 degrees, put it into radians. That way when we do our conversion, we'll know what the arc length is. We can use the radians answer. Thank you. Okay, so what we're really doing is we're going to take that radius and multiply it by 25 pi over 36. So the arc length in this case is 17.9 centimeters. Determine the central angle in radians. This time I'm telling you it has an arc length of 3 centimeters, but the circle has a radius 10 centimeters. So I almost feel like I'm insulting you by asking you to do this kind of thing now, but if I don't, people get to their homework and they go, Mr. Joyce, you never taught us this. Actually, you guys don't talk like that. I don't know why, but that's like my teenager voice. Sorry. Okay. So I have theta is 3 over 10, or 0.3 radians. Okay. And again, if I needed to, I could convert 0.3 radians into degrees, and I could tell you how many degrees that arc made. So going from degrees to radians and radians to degrees, we're going to be using radians a lot, so don't worry if it's still something kind of fuzzy. We're going to use them a lot. But also using radians to get an arc length, those are the two things so far. The rest of it, we're going to talk about angles and standard position. Are there any questions so far? Easy peasy? Okay. Okay, so we want to talk about angles and standard position then. We could draw an angle any way we want and give it the same value, like these 4 shapes I'm showing you on the board here. So to be standardized the way we draw angles, first thing we're going to do is need a bit of terminology. We call this angle here, this the terminal arm, and we call this the initial arm. So like the word initial, that's the start. That bottom arm, it's where the angle starts, and the terminal arm is where you stop. I don't know why they don't just say starting arm and stopping arm, but now you know when you read it. Terminal is the end, initial is where you start. We also are going to talk about these angles in 4 quadrants, and this is where we start. So we go 1, 2, 3, and 4. Okay. And the other thing you need to know about when we draw the angles is a clockwise rotation. Okay. That's actually a negative angle. And a counterclockwise will be a positive angle. So those are some of the rules that we're going to use for standard angles. Now let's draw a couple just so you can see what I'm talking about. Okay, so 120 degrees, this is where we always start. This is 0 degrees. That's the initial arm for everyone. That's 0 degrees. That's 90 degrees. That's 180. That's 270. So if I'm doing 120 degrees for you, it's going to look about like this. I'll do negative 135 in red just so you can pick it out. But if I go negative, this time I'm changing the rotation. I'm going to go the other direction. I'm going to go clockwise. So this would be negative 90. This would be negative 180. Negative 270. And this would be all the way around to 360 if I did make it all the way there. So at negative 135, it's going to show up right in the middle here. Now, here's the part where you have to, usually people start out with a conversion, but I'll tell you, it really pays. It'll annoy you a lot less if you start embracing radians and you just get used to the fact that your life is going to be filled with them. So, I mean, this is what students do. They go like this, and then they convert it to degrees. That's fine. You'll be able to do everything. It's just it takes you that much longer, and it annoys you that much more. So the reason I told you earlier, my favorite one to talk about is pi, and it looks like this, is when you're trying to figure out where's pi over 6. In my head, this is what I do. I've got to cut it into 6 pieces then. So this first one right here, that's where I'm going to stop. Right? If I start to think about cutting up half a circle for each pi that I'm using, that way I don't have to make those conversions and do the extra step. So pi over 6 would be here. So if I'm doing negative 5 pi over 4, can somebody explain that to me in kind of like a pizza slice sort of way? You can use some fractions, like describe for me how I walk through the circle when I do it. Like how much do I take? Yeah. Is it in the third quadrant? It would be if it was positive 5 pi over 4. It's in the second quadrant. Yeah, how did you get there? Just magic, just genius. What you're going to need to think about is, I think about this myself as negative. I split it. You'll get the hang of it too pretty quick. I split it like this because 4 pi over 4 is a half circle, and then pi over 4 is a quarter circle. So that's telling me go back by a half a circle. That's that piece right there. Then go back by a quarter of that semicircle. And that right there is negative 5 pi over 4. Again, there's nothing wrong with doing the conversion, but I promise you, you will like doing it better if you get comfortable with radians. They're not going away. So your turn. Try plotting these, one set in degrees, the other set in radians. All right, so 30 degrees is right about here. 390, in my mind, I'm thinking 360 degrees plus 30 more. So I end up doing this. I go around and, oh, there they are. Negative pi over 6, sorry, I got 7 pi over 6 first. So that's going to be, again, in my head, I split that into pieces like this so that I can move in semicircles. That's one semicircle plus a sixth of the semicircle. So 7 pi over 6 is here. And negative pi over 6 is going to be this one down here. So that's going backwards. All right, so anybody notice something there? Yeah, sure. They're the same in the first graph. Different numbers, same standard position. So that's what we call them is if two angles are coterminal if they share the same terminal arm. Okay, so let's find a coterminal angle. From 35 degrees, can someone give me a coterminal angle? 395, genius. How'd you do it so quick? Good, yeah. Oh, this one's going to be tougher. Negative 9 pi over 4. Anyone want to take a shot? How would you find a coterminal angle there?
1 over 4. 1 pi over 4.
Negative pi over 4.
Negative pi over 4. Yeah, that's right. So this time, what you're doing is you're not working with 360. You're not working with 360, but you're working with 2 pi. So here, if you just add, say for example, 8 pi over 4, you end up at negative pi over 4. So you draw it, they would end up on the same standard position, even though those numbers are different. So how do you find one quickly? Plus or minus 360 degrees. We could subtract it, that'd be fine too. Or plus or minus 2 pi when we're dealing with radians. So one thing we're going to run into in this unit then, that idea of finding many solutions, we want to be able to express our answers, so we don't have to write them all out. That'd be a long detention if I made you write out all the coterminal angles. What I'm going to have you do instead is write it this way. 35 degrees plus or, well actually we don't even need to do plus or minus, we can just do plus 360 n, where n is an integer. Okay. You're going to see it in calculus as the shortcut. This means where n is an integer. This is n is an element, and that's the symbol for integers in mathematics. So either is fine for you. I'll keep writing out the long form of English, even though it drives me crazy. Okay? How could you write the general solution for the one we found up here? How could you? If I said, here's the angle you start with, can you write a general solution down? Okay, what would it look like? Sure, negative pi over 4 works, but it'll be the same thing if we start with the one we had. And then what do I do to it? Yeah. 2 pi n. Oh, I hate this part. You know this used to be worth a point on the provincial exams? Writing down where n is an integer used to be worth a point. Well, 2 pi is 360 degrees, so, all right. I thought this year might be the first year I could get away with it, but I guess I'm going to have to do my coterminal dance for you. So here's my angle from me to you, and that's how you find a coterminal angle. Doesn't matter if it's 2 pi or if it's 360 degrees. They're all going to end up in the same spot, right? So that's why I added 2 pi in this case. That's one full turn. 360 is one full turn. Yeah, I'm a terrible dancer, I know. All right, so we're really only going to use coterminal angles for one kind of goal, and it's getting us to what we call a principal angle. And this is the one which is between 0 and 360 degrees. And again, now that I'm trying to get you guys climatized to radians, it's 0 to 2 pi. Why do you think that is? It's less complicated. 0 to 360 is the world that most of us lived in until today kind of thing, right? Like if I told you, 35 degrees or 395 degrees, you guys would probably rather deal with 35, right? And you know where that is, you can picture it. 395 is a little harder. Okay, so that's what I want you to be able to do then is, out of all these angles you're looking at, find me the principal angle, which means you're going to do your coterminal dance until you end up with an angle which is between 0 and 360 or 0 and 2 pi. because we don't want to work with negative 1550. We want to shrink it down until we get to the same spot in a smaller principal angle. All right, so how are you getting them? Hopefully this didn't take as long as it looks, because there's a trick to it. How do you do it real quick? Just keep taking 360 away. So where do you end up? Sorry? Okay, what about this one? You're adding 360 this time. Where do you end up? Yeah, it should be 250, right? The negative 110 means you've got to go one more, because the principal angle is from 0 to 360. Okay? 25 pi over 8. Sorry, I just heard a little, it was 9 pi over 8. And negative 12 pi over 7. 2 pi over 7. Okay? So what I'd be doing, if you're having trouble with radians here, this one I'm subtracting 8 pi over 8. So you're going to go, that'll take you from 25 down to, take 8 of those away, 17, thank you. And then 8 more away would take you to 9, where then you're stopped, you're in the range. And then again here, I'd be dealing with 7 pi over 7, and I'm adding to it. So it'll go from negative 12 to negative 5 to 2, and that's where we could stop. Okay. In your calculator, just don't put the pi in, and you can keep adding or subtracting until you get in the range, because you obviously with a pi, your calculator's going to have some troubles. There'll be lots of decimals in there. Okay. So here's one of the reasons you need to know a principal angle. We should be able to find these without having to do this whole graphing business. The standard angles, the pictures look pretty, but here's one of the reasons you want to know. So without graphing, where do you think 690 degrees would be? Fourth quadrant, okay? How did you get it? You should have a principal angle of 310. Sorry, 330. So if you know 330 degrees, hopefully you can then picture that in the quadrants and say to yourself, 330 degrees is going to be over here, something like this, in quadrant number 4. Okay? So 1770, what's the principal angle? $310? Okay, so 310, which quadrant is that in? Yeah, it's in quadrant 4. Okay, you brave enough to do some radians? 13 pi over 4. Okay, let's walk through this one together then. 13 pi over 4. 2 pi's are going to be 8 pi over 4. So that takes me to 5 pi over 4. Am I in range now? I'm in range, so I can stop. That is a semicircle and a quarter more of a semicircle. So this is where I'd be in quadrant 3. Okay. Set negative 17 pi over 3. Again, 2 pi is how I have to spin this. So I'm going to be dealing with 6 pi over 3. And this time I have to go up. So 17 pi over 3. This time I'll add 6 pi over 3 to it. And I'll be at negative 11 pi over 3. Still not there. Still not there. But now I'm there. Pi over 3 is in range. Here's where we'll find it. Pi over 3 is right there. Now, if you're in survival mode and you're like, I don't hate radians, you can always rely on converting it to degrees and then using the degrees to do it. But anyways, make it a note that you're going to want to get comfortable with them. So you still want to practice. Okay, so there's a quadrant 1 angle. So finally, we have a reference angle. This is the last thing we need to learn about today, and that's all the terminology and things that fall onto standard positions. The reference angle is the angle between the terminal arm and the x-axis. And it is one that's going to creep up for quite a bit more of trig, so probably the most important part of today's lesson. So I'm going to illustrate to you why that is. Somebody with a calculator, what's the sine of 30 degrees? 1/2, yeah, it should be 1/2. So what about the sine of 150 degrees? 1/2. Okay, what about 210? Oh, it's not 1/2 this time. It's negative 1/2, yeah. And then if you put in 330 to your calculator. So why are these things coming up with the same value? The only difference is the sign. Well, they all share the same reference angle, and that's what I want to show you how to find. So here's 30 degrees, 150 degrees, 210 degrees, and 330. Here is the angle between the terminal arm and the x-axis. So each of these is the reference angle. And the only thing that's going to change on us is whether it's positive or negative. So basically what we've been able to do in this lesson is you can give me any angle you want, and right now you should be able to spin it coterminal until you end up with a principal one. Now your world of trig has shrunk to 0 to 360. Now I'm about to show you how to shrink that 0 to 360 down to 0 to 90, because we're only interested in that one little angle between the angle and the x-axis. So how do you figure out what the reference angle is? People like this formula. I'm not going to say you have to use it, but if you look, this is 180 degrees here, and I'm taking away the angle. So if you know it's a quadrant 2 angle, 180 minus the angle will put you on the reference. If you have a quadrant 3 angle, you take 210 minus the 180, and it's going to give you these 30 degrees in here. So that would be angle minus 180 equals reference angle. I'm not one for using the formulas myself. Here, of course, it's nice and easy. I usually just calculate it off of the picture, so don't feel like you have to copy in those formulas, but some people sleep better at night having formulas. Okay, and then here, how do you think we could calculate, if you know it's a quadrant 4 angle, how could you find its reference? Yeah, 360 minus the angle itself. And of course, if I was dealing with radians, it wouldn't be 180, it would be pi, and if it wouldn't be 360, it would be 2 pi. Yeah, so we could switch this around and do the exact same thing for radians, but I'll leave it in degrees where hopefully you're more comfortable. Okay, so last task of the day, find me the reference angle, once in degrees, once in radians. Okay, just to make sure you're on the right track, I'll walk through 500 with you. This uses all of our skills today. Coterminal, to get me a principal, that turns out to be take away 360 degrees, and I land on 140, which is my principal angle. Then in my head, I'm going to picture where is 140? 140 is somewhere over here. So if that's 140 degrees, and that's 180 degrees, yeah, what's the reference angle? 40, that's right. Okay, 11 pi over 3. Just curious, how many people are they're going to convert it? You're going to go right to degrees. No shame, I just want to know. No? Okay, good for you. 11 pi over 3. It's not in range right now, so what I'm going to do is take away, 6 pi over 3. And I end up with 5 pi over 3. that's in range. So now I'm good. Because 0 to 2 pi would be 0 to 6 pi over 3. 5 pi over 3 is in there, so I'm okay. That's my principal angle. Oops, principal angle. And if I was to figure out 5 pi over 3, that's like 3 pi over 3 plus 2 pi over 3. That's 1 semicircle and 2/3 of a semicircle. So here's where 11 pi over, there's where 5 pi over 3 lives. It also happens to be where 11 pi over 3 lives. So all the way up there is 2 pi over 3. Down here is 5 pi over 3. So what's left over? Yeah, just pi over 3. Oh, I see. You're thinking about the, yeah, we're just taking the absolute value of the sign. We're not interested in, don't worry about the direction it goes as positive or negative. The reference angle is always a positive acute angle.
Does that only apply to this angle?
Yeah, so even though it's upside down, we're just saying that's how you visualize its quantity. But yeah, that's you know what, in whatever many years I've done math, that's the first time anyone's ever picked up on that. So yeah, that's good. Okay, so don't worry about the direction. Clockwise, counterclockwise is always positive for a reference angle.